The Milky Way, our home in the vast universe, is one of the greatest mysteries humanity has ever explored. Within this galaxy, billions of stars shine, trillions of planets quietly orbit, and countless scientific stories await our decoding. But what exactly is the Milky Way, and what makes up such an immense and complex structure? The Milky Way, our galaxy, is a vivid example of a barred spiral galaxy, one of the most common types of galaxies in the universe. With an impressive diameter of approximately 200,000 light-years, the Milky Way is not only home to the solar system, but also harbors hundreds of billions of stars, trillions of planets, and countless clouds of interstellar dust and gas. Light, the fastest-moving entity in the universe, still requires 200,000 years to traverse the entirety of this colossal galaxy. A distinctive feature of the Milky Way is the bright bar of stars running through its center, spanning about 13,000 light-years. This bar not only helps maintain the galaxy's characteristic shape, but also plays a role in directing the spiral arms, regions where vigorous star formation occurs. These arms are a brilliant ensemble of young, luminous stars interspersed with cosmic dust and interstellar gas, creating stunning yet enigmatic visuals. The formation of the Milky Way traces back to over 13.5 billion years ago, shortly after the Big Bang. Gravitational forces attracted clouds of cosmic gas and dust, merging them into the massive and complex structure we see today. Throughout its evolution, the Milky Way has also undergone mergers with smaller galaxies, incorporating additional matter and energy that shaped its current structure. At the galaxy's center lies a mysterious region, home to a supermassive black hole named Sagittarius A star. With a mass equivalent to 4.3 million suns but compact in size, this black hole is surrounded by an intensely luminous accretion disk. The area near the center also hosts thousands of stars, some of which travel at incredible speeds under the influence of immense gravitational forces. The Milky Way is not only a home for ancient stars, but also a nursery for new stellar generations. Regions like interstellar gas clouds and nebulae serve as cradles for young stars, where nuclear fusion reactions ignite to light up the universe. These areas are often detected through infrared or radio wave emissions, as dense dust obscures visible light. Beyond the galactic disk, the Milky Way is surrounded by a vast halo containing globular clusters and a significant amount of dark matter. Dark matter, which constitutes up to 90% of the galaxy's mass, does not emit light, but plays a crucial role in maintaining the galaxy's structure and gravitational balance. Scientists deduce the existence of dark matter through the orbital motions of stars and interstellar gas. Each part of the Milky Way carries its own stories of origin and evolution, from ancient stars that have existed for over 13 billion years to planets that may harbor signs of life. Exploring our own galaxy not only deepens our understanding of the universe, but also unveils secrets about humanity's existence in this vast expanse of space. The Milky Way is a colossal spiral galaxy, akin to a vast kingdom in the universe, encompassing a diverse array of cosmic components. With approximately 200 billion stars, this galaxy ranges from massive, brilliant stars shining like cosmic beacons to small, dim stars quietly tucked away in the dark corners of the galaxy. Each star, whether large or small, tells its own story of a life cycle, from formation, shining brightly, to exhausting its energy and entering its final stages as white dwarfs, neutron stars, or even black holes. These cycles not only enrich the galaxy's components, but also play a vital role in the growth and restructuring of the Milky Way over billions of years. In addition to luminous stars, the Milky Way is home to 25 to 100 billion brown dwarfs, often referred to as failed stars. Their masses are insufficient to ignite nuclear fusion, preventing them from shining as brightly as ordinary stars. However, brown dwarfs play an important role in the galaxy's structure, helping to maintain gravitational balance and enriching the diversity of the cosmic ecosystem. They stand as evidence of the limits in star formation processes and the ways gravity shapes celestial bodies. Beyond stars, the Milky Way serves as a vast museum housing over 1 trillion planets, ranging from giant gas planets like Jupiter to small rocky ones. Some of these planets may lie within habitable zones, where climate conditions and distances from parent stars are conducive to sustaining liquid water, a key factor for supporting life as on Earth. These planets are the focus of humanity's quest for extraterrestrial life, offering new hopes for the future of space exploration. In addition to stars and planets, the Milky Way contains massive clouds of gas and cosmic dust, the raw materials for forming new stars and planets. These clouds are the sites of star formation, where gravity compresses gas and dust to trigger nuclear fusion. Gas clouds, along with vibrant nebulae like the Orion Nebula, create stunning and wondrous landscapes, showcasing the dynamism of a galaxy constantly in motion and renewal. Moreover, within the vast expanse of the Milky Way exist countless small but significant celestial bodies, such as comets, asteroids, and meteoroids. Despite their small size, these objects play critical roles in delivering organic materials to nascent planets, contributing to the potential formation of life. Comets, with their elongated orbits and luminous tails, not only enrich the cosmic scenery, but also serve as witnesses to the remnants of material from the early days of the solar system. All these components, from the brightest stars to the tiniest specks of dust, come together to form the magnificent structure we call the Milky Way. Far from being just a collection of astronomical objects, this galaxy operates as a wondrous machine governed by the laws of physics, from gravity and the interaction of dark matter to the endless regeneration of stars and planets. The Milky Way, in its complexity and grandeur, is not only a cradle for our existence, but also a panoramic portrait of the universe's motion and evolution. From the radiant light of stars to the mysterious darkness of dark matter, from promising planets to cosmic debris, the Milky Way is a vivid testament to the beauty and wonder of space that humanity is exploring step by step. The matter within the Milky Way is unevenly distributed, concentrating in regions with distinct characteristics and roles, forming a complex and vibrant galactic structure. The core of the Milky Way, or the galactic nucleus, is the area of greatest matter concentration and hosts the most intense physical phenomena. Here, enormous globular clusters, assemblages of hundreds of thousands of ancient stars, dominate the space. Some stars in this region have existed for over 13 billion years, harking back to the early days of the universe. Besides these clusters, the core of the Milky Way houses Sagittarius, a star, a supermassive black hole with a mass approximately 4.3 million times that of the Sun. This black hole acts not only as a gravitational heart, but also strongly influences the movement and structure of the entire galaxy. The core is not just a dense and ancient matter reservoir, but also a center of complex physical interactions. Stars in this area move at incredible speeds around the central black hole, creating a chaotic gravitational dance. Additionally, the galactic core is enshrouded by dense gas clouds and cosmic dust, obscuring visible light. However, using infrared and radio wave observation technology, scientists have managed to penetrate this dusty veil to uncover the secrets hidden within. In contrast, to the dense and aged matter concentration at the core. The outer regions of the Milky Way are livelier and more youthful. Here, star-forming regions erupt like stellar factories, where dense interstellar gas clouds and cosmic dust serve as the main ingredients for the creation of young stars. These stars often shine more brightly and have higher temperatures than the older stars in the core, illuminating their surroundings like cosmic lighthouses, guiding through the universe's dark night. The outer regions are not just star-forming sites, but also home to the galaxy's prominent spiral arms, including major ones like the Perseus Arm and Scutum Centaurus Arm. These areas host most of the young stars and gas clouds, creating a colorful and dynamic galactic portrait. It is in these outer regions that planetary systems like our solar system exist. Here, the balance between the bright light of young stars and the encompassing darkness of cosmic voids creates an intriguing interplay. Matter in the Milky Way is not confined to the core and spiral arms. Surrounding the galaxy is a faint but significant halo containing ancient globular clusters and a large amount of dark matter, a mysterious substance that scientists are still investigating. While dark matter does not emit light, it plays a crucial role in maintaining the galaxy's structure and gravitational equilibrium, ensuring the Milky Way's stability in space. The diverse distribution of matter within the Milky Way, from its aged core to its vibrant outer edges, from radiant stars to enigmatic dark matter, is not merely a structural feature, but a testament to the galaxy's ongoing motion and evolution. Every region, every component, plays a unique role, collectively creating a cosmic kingdom full of wonder, beauty, and fascinating stories about the formation, evolution, and future of the universe. The Milky Way is a majestic symbol of the universe, embodying immense scale and structural complexity. With a diameter of up to 200,000 light-years, the Milky Way is not only one of the largest galaxies in the local group, but also one of the most spectacular cosmic systems observable. However, the primary spiral disk of the galaxy, containing most stars and planetary systems, is only a part of its entirety. The faint halo surrounding the galaxy extends much farther, surpassing the primary disk's size and expanding the true scale of the Milky Way to limits invisible to the naked eye. This halo, though not brightly illuminated, holds many secrets and plays a critical role in the galaxy's dynamics and stability. With the aid of telescopes and advanced observation technologies, scientists have discovered that the halo is not an empty void. Instead, it contains globular clusters, dense, ancient star groups, some of which have existed since the early universe over 13 billion years ago. These clusters, along with rogue stars, are vivid evidence of the galaxy's evolutionary processes. More intriguingly, the halo reveals part of the Milky Way's history, particularly its past collisions and mergers with smaller galaxies. Some globular clusters and long stellar streams have been identified as remnants of satellite galaxies consumed by the Milky Way's powerful gravitational forces. These fragments, once part of other galaxies, have now merged into the Milky Way's structure, adding material and energy, shaping the galaxy as it is today. Beyond the halo and the main disk, the Milky Way extends further into a dark halo, a vast region containing dark matter, a substance that cannot be directly observed but whose presence is inferred through gravitational effects. This dark halo may stretch up to 2 million light-years, nearly 10 times the size of the main disk. While it does not emit light, dark matter plays an essential role in maintaining the galaxy's structure, keeping its stars and spiral arms from dispersing under centrifugal forces. Another indicator of the Milky Way's vast scale is its mass, estimated to range between 1 and 1.5 trillion solar masses. This mass includes not only stars and planets, but also gas clouds, cosmic dust, and a significant amount of dark matter. This immense mass helps the Milky Way maintain its gravitational pull on its components while interacting with neighboring galaxies in the local group, such as the Andromeda Galaxy. The grandeur of the Milky Way is reflected not only in its physical size, but also in its influence. The stars, planets, and matter within the galaxy operate under distinct physical laws, while intricately interconnected in a complex system. From the galactic core, home to the supermassive black hole Sagittarius A, to the distant outer reaches of the halo, every component holds unique significance, contributing to the galaxy's perpetual motion. The Milky Way, with its immense scale and diverse structure, is not just a galactic system, but a vibrant portrait of the universe's history and evolution. From ancient collisions to the formation of new stars, this galaxy continually tells captivating stories, demonstrating the vastness and wonder of space. Every step in the journey to explore the Milky Way unveils new secrets, fueling humanity's aspiration to understand its place in the boundless universe. Hidden deep in the center of the Milky Way lies a strange and incredibly powerful phenomenon: the supermassive black hole known as Sagittarius, a star. Although invisible to the naked eye, it is the heart of our galaxy, where an immense gravitational force dominates everything. So, what exactly is Sagittarius A star, and why does it hold such an essential role in the universe? Sagittarius A star is a supermassive black hole located at the center of the Milky Way, one of the most prominent and mysterious features of our galaxy. While invisible to the naked eye, Sagittarius A star wields immense power, controlling the motion of stars and matter across a vast region. With a mass equivalent to approximately 4.3 million times that of the Sun, this black hole not only exerts a significant gravitational influence, but also warps space and time around it. A clear testament to the power of Einstein's theory of general relativity. One of Sagittarius A star's most remarkable features is its accretion disk, a region where matter such as gas and dust is drawn toward the black hole. As particles fall into its immense gravitational pull, they spiral around at incredible speeds, reaching hundreds of thousands of kilometers per second, before disappearing into the black hole. Despite having a diameter of only about 16 million kilometers, smaller than Mercury's orbit around the Sun, this accretion disk is a powerful center of energy emission. As matter is compressed and heated to extreme temperatures, it emits electromagnetic radiation, ranging from X-rays to visible light, illuminating the surrounding space and allowing astronomers to pinpoint Sagittarius A star. Despite being at the center of a massive galaxy, Sagittarius A star is considered a quiet black hole compared to other supermassive black holes in the universe. It does not frequently consume large amounts of matter as more active black holes do, which often emit intense energy bursts and produce awe-inspiring phenomena like quasars. However, when matter enters its influence, the process still generates short but powerful bursts of energy, releasing X-rays and other forms of radiation, providing scientists with valuable clues to study this enigmatic black hole. The existence of Sagittarius A star has been confirmed through long-term studies of the orbits of stars near the galactic center. A notable example is the star S2, which orbits Sagittarius A star in an elongated elliptical path that takes 16 years to complete. The star's tight orbit indicates that it is entirely dominated by an invisible and supermassive object, Sagittarius, a star itself. Observations like these not only enhance our understanding of gravitational forces, but also provide opportunities to test physics theories under extreme conditions. Furthermore, recent bursts of radiation from Sagittarius A star have yielded crucial information about how the black hole interacts with its surroundings. Each time a small amount of matter is drawn in, it produces waves of energy that briefly illuminate the galactic center. These events, recorded by modern telescopes like the Chandra X-ray Observatory and the Very Large Telescope, offer deeper insights into the activity of this quiet black hole. Sagittarius. A star is not just the gravitational center of the galaxy, but also a window into a broader understanding of the universe. Studies of this black hole have provided significant information about the structure and dynamics of the Milky Way and helped clarify the nature of supermassive black holes. Despite being a symbol of absolute darkness, Sagittarius, a star, is a powerful inspiration for humanity's relentless pursuit of the great mysteries of the cosmos. Sagittarius. A star, the supermassive black hole at the center of the Milky Way, has existed for billions of years, but was only directly confirmed in 2022. This milestone was achieved through the extraordinary efforts of scientists worldwide and the advanced technology of the Event Horizon Telescope (EHT) network. For the first time in history, humanity has seen visual evidence of a supermassive black hole within its own galaxy, marking a turning point in the exploration of the universe. The first image of Sagittarius A star shed light on long-standing mysteries about the center of the Milky Way. In the photograph, a faint glowing ring surrounds a dark central region, the shadow of the black hole. This glowing ring is formed by light bending as particles spiral around the black hole at near-light speeds. This phenomenon, known as gravitational lensing, not only provides direct evidence of Sagittarius A star's existence, but also helps scientists determine its critical properties. From these observations, researchers have precisely measured the black hole's colossal mass, about 4.3 million times that of the Sun, and the rotation of its surrounding region. These invaluable data reinforce theories about black holes and gravity. Capturing an image of a black hole 27,000 light-years away posed significant technical and collaborative challenges. The EHT network consists of a system of radio telescopes located across the globe, from the icy Arctic to the arid Atacama Desert. Combining these telescopes creates a virtual telescope the size of Earth, offering extremely high resolution to observe distant and tiny objects like Sagittarius A star. Collecting and synchronizing data from these telescopes required exceptional precision, with petabytes of data processed and analyzed over years to produce the first image. This discovery is not only a scientific achievement, but also paves the way for further studies on the nature of black holes. Black holes are not merely matter vacuums in space, but play a crucial role in the evolution of galaxies. EHT studies have provided the first glimpse of how Sagittarius A star interacts with its surroundings, from generating powerful energy streams to shaping the galaxy's structure. These findings also open the door to investigating other black holes in the universe, particularly in neighboring galaxies, and those at the centers of distant galaxies. This accomplishment holds even greater significance when placed in the context of astronomy's history. From the first hypotheses about black holes' existence, based on Einstein's theory of general relativity, to the discovery of Sagittarius A, in the late 20th century, humanity has come a long way in understanding these mysterious regions of space. The first direct image of Sagittarius A star is not just a triumph of science and technology, but also a testament to the power of international collaboration and the unyielding drive to explore. Sagittarius A star is no longer just a theoretical concept, but a vivid symbol of what humans can achieve when intelligence and technology unite. Observing this black hole directly not only illuminates cosmic mysteries, but also opens new doors for continued exploration. It serves as a reminder that in the vast and enigmatic universe, every scientific advancement brings new answers and raises new questions, propelling us further in our quest to understand the essence of space and time. Surrounding Sagittarius. A star is a captivating region where over 6,000 stars orbit within a radius of 3 light-years from the supermassive black hole. This unique space, entirely governed by Sagittarius, a star's intense gravitational force, creates dynamic and complex trajectories. These stars not only display a vibrant spectacle, but also act as physical witnesses, helping humanity explore and understand the nature of a supermassive black hole. One of the most notable stars in this area is S62, the fastest-moving star known to date. When closest to Sagittarius, A star, S62 reaches a velocity of 6.7% of the speed of light, about 72 million kilometers per hour. This immense speed is a testament to the black hole's staggering gravitational pull, pushing the limits of what gravity can exert on a celestial body. The existence of S62, along with other stars in the region, provides direct and convincing evidence of Sagittarius A star's presence, which was previously only hypothesized through theoretical models. The orbits of these stars are far from the simple paths of typical planets. As stars move close to the black hole, they are influenced by Einstein's relativistic effects. In the curved fabric of space and time, their trajectories become irregular and unpredictable. Phenomena such as time dilation and gravitational redshift become more apparent than ever. These observations not only provide experimental evidence supporting general relativity, but also create opportunities to test physics theories under extreme conditions found in few places in the universe. Beyond validating physical theories, these stars serve as vital beacons, guiding scientists in uncovering the mysteries surrounding the supermassive black hole. Every orbit and anomaly in their motion reveals insights into how matter and energy interact with intense gravitational forces. For instance, by tracking these movements, astronomers can create precise maps of the space around Sagittarius, A star, further understanding the distribution of matter at the galaxy's core. This knowledge is crucial for developing detailed models of the Milky Way's evolution and understanding the role of supermassive black holes in shaping cosmic structures. These stars also hint at dynamic processes near the black hole. The presence of young stars in the galactic core, an environment typically inhospitable for star formation, raises questions about how they formed or arrived there. One hypothesis suggests they might be remnants of star clusters drawn in by Sagittarius A star's gravity, or they formed from material in the black hole's accretion disk. These studies not only deepen our understanding of the harsh environment surrounding Sagittarius A, but also help unravel the mysteries of how extreme gravitational forces influence the survival and motion of celestial bodies. The orbits of stars around Sagittarius. A star are not just spectacular displays of physics, but also keys to unlocking new understandings of the universe. From confirming the presence of a supermassive black hole to testing physical theories in extreme environments, these stars contribute significantly to the advancement of astronomy. Their unique trajectories not only illuminate the nature of Sagittarius A, but also fuel humanity's relentless curiosity to explore the unknown. The Milky Way, our galaxy, is not just a dazzling canvas of billions of stars, but also conceals a complex, intricate structure akin to a masterpiece of cosmic architecture. What gives it its characteristic spiral shape and majestic structure? The Milky Way is a prominent spiral galaxy with a structure comprising 4 main arms: Scutum Centaurus, Perseus, Sagittarius, Carina, and Norma. These arms are not only the concentration hubs for most stars in the galaxy, but also dynamic centers where intense star formation processes continuously occur. Each spiral arm has unique characteristics, contributing to the complexity and diversity of the galaxy. Scutum Centaurus. The largest and longest arm, Scutum Centaurus, is the largest spiral arm in the Milky Way, stretching from near the galactic center to the distant outskirts. This arm is a rich region, home to numerous massive star clusters and radiant nebulae, serving as star factories. Here, millions of new stars are formed from clouds of cosmic gas and dust, creating brilliant regions observable through telescopes. Star clusters in the Scutum Centaurus arm often consist of young, bright, and hot stars, highlighting the dynamic beauty of the galaxy. Perseus, the arm of youth and star formation. The Perseus arm stands out for its abundance of young stars and vibrant star-forming regions. It is one of the brightest and most recognizable parts of the galaxy, thanks to its large star clusters and distinctive nebulae. Young stars in the Perseus arm are scattered across regions rich in gas and dust, providing ideal conditions for the nuclear processes that birth new stars. Viewed through powerful telescopes, the Perseus arm appears as a vivid, colorful band, showcasing the vigorous life of the Milky Way. Sagittarius, Carina, and Norma, the hubs of creation. The Sagittarius, Carina, and Norma arms lie near the galactic center, where large amounts of gas and cosmic dust accumulate. These regions are particularly active, hosting large-scale star formation processes. Their proximity to the galactic center means they often contain dense clouds of gas and massive nebulae, serving as abundant sources of material for new stars. However, the environment here is harsh, with strong gravitational forces and violent astronomical events, such as supernova explosions. Orion Arm, the home of the solar system. Amid these majestic main arms, the Orion Arm, a smaller spur arm, holds special significance for us. It is the home of the solar system, located approximately 27,000 light-years from the galactic center. This location is considered ideal, being far enough to avoid the intense and hazardous activities near the galactic core, yet close enough to benefit from the abundant resources in surrounding star-forming regions. This stable position has allowed Earth, a planet of life, to develop and thrive over billions of years. Harmony in a complex structure. The spiral arms of the Milky Way not only create its physical structure, but also reflect the galaxy's constant motion. These arms are not static, but continually change, interact, and evolve, achieving a harmonious balance among gravitational forces, star formation, and other astronomical activities. Each arm, whether large or small, contributes to the story of the Milky Way's formation and evolution, a galaxy that is not only our home, but also a mysterious wonder of the universe. In conclusion, the 4 main spiral arms, along with the Orion Spur, define the beauty and vitality of the Milky Way. From the brilliant regions of nebulae and star clusters to the quieter environment of the Orion Arm, home to the solar system, the Milky Way is a vivid testament to the complexity and marvel of the cosmos. These arms are not only reservoirs of matter, but also foundations for creative and evolutionary processes spanning billions of years. The primary structure of the Milky Way is concentrated within a vast galactic disk, encompassing most of the galaxy's mass and hosting its most significant activities. This galactic disk is not merely a physical structure, but the center of vibrancy and evolution. It is divided into two main components, the thin disk and the thick disk, each with unique characteristics and contributions to the galaxy's development. The thin disk, youthful and dynamic. The thin disk is the more vibrant and youthful part of the galaxy, containing about 80% of the Milky Way's mass. With a thickness of only about 1,000 light-years, it is home to young stars, interstellar gas clouds, and actively star-forming regions. The thin disk is considered a natural laboratory, where famous nebulae such as Orion and Eagle cradled the birth of new star generations. Here, massive gas clouds and cosmic dust interact under the influence of gravity, initiating the star formation process. Stars in the thin disk are often bright and hot, radiating brilliant light that accentuates the vitality of the Milky Way. Additionally, planetary systems have been discovered in this region, emphasizing the thin disk's role in nurturing both stars and new planets. Scientists are particularly interested in the thin disk, as its diversity and energetic nature provide rich data for studying the evolution of stars, planets, and the galaxy as a whole. The thick disk, the ancient history of the galaxy. In contrast to the thin disk's youthful energy, the thick disk is more subdued and ancient. With a thickness of about 4,000 light-years, 4 times that of the thin disk. This region contains older stars, some with lifespans of billions of years. The thick disk has significantly less interstellar gas, with little to no ongoing star formation. It preserves witnesses of the early Milky Way, when the galaxy was just beginning to form and grow. Stars in the thick disk often have eccentric orbits, differing from those in the thin disk. Their chemical composition is distinct, with lower levels of heavy elements, reflecting a period in the universe's history when it was still young and had not undergone many cycles of star formation. Studying the thick disk not only provides insights into the Milky Way's past, but also offers crucial information for reconstructing the formation of spiral galaxies like ours. The interplay of the two disks. Although they have distinct characteristics, the thin and thick disks do not exist independently, but interact and complement each other, forming a harmonious system. The thin disk represents vibrancy and renewal, where the galaxy continuously evolves with the emergence of new star generations. Meanwhile, the thick disk serves as a historical archive, providing valuable clues about the galaxy's early formation and development. This interplay creates a comprehensive picture of how the Milky Way operates and evolves over time. Activities in the thin disk not only drive current development, but also restructure old material from the thick disk, establishing an incredible cyclic process. This demonstrates that despite their stark differences, the two parts of the galactic disk remain tightly interconnected, ensuring the Milky Way's stability and sustainable growth. The galactic disk's role in life. The galactic disk, particularly the thin disk, plays a crucial role in forming and sustaining environments for life. Our solar system resides in the thin disk, at a location favorable for avoiding unstable regions near the galactic center, while being close enough to draw from the galaxy's abundant resources. This positioning has provided Earth with ideal conditions for life to develop over billions of years. In conclusion, the galactic disk is not just the central structure of the Milky Way, but also a vivid representation of the galaxy's motion, evolution, and history. From the brilliant young stars in the thin disk to the ancient witnesses in the thick disk, each component contributes to the collective story of the cosmos's complexity and wonder. The Milky Way is not only defined by its spiral arms and galactic disk, but also features a significant structure known as the galactic bar. This characteristic, common in barred spiral galaxies, sets the Milky Way apart with a central bar extending about 13,000 light-years from the galactic center. The bar is not merely a structural component, but serves as the spine, coordinating and maintaining the galaxy's stability. The galactic bar, the engine of material flow. The Milky Way's galactic bar is composed of millions of bright stars and large amounts of cosmic gas and dust. Stars and matter within the bar move in unique orbits, forming a steady flow of material from the outer regions to the galaxy's center. This flow enables the bar to act as a powerful engine, driving the movement of gas and dust and replenishing essential resources for supermassive black holes and dynamic star-forming regions at the galactic core. This process keeps the galactic center vibrant, while ensuring the circulation of matter throughout the Milky Way. Gas and dust funneled into the center are compressed under extreme temperature and pressure, creating an ideal environment for new stars to form. These stars may grow into massive star systems or even influence the structure of surrounding spiral arms. Interaction with spiral arms. A cohesive connection. The galactic bar does not exist independently, but is closely linked with the galaxy's spiral arms. This interaction plays a crucial role in maintaining the Milky Way's characteristic shape. The bar acts as a stable framework, anchoring the spiral arms as they extend from the center to the galaxy's outer regions. This connection ensures the continuous circulation of matter in the Milky Way. Dust and gas flow from the bar to the spiral arms, where they contribute to star formation. Conversely, older or inactive matter is drawn back to the center, restarting the galaxy's life cycle. This perpetual cycle fuels the Milky Way's vitality, allowing it to evolve over billions of years. Radiance from the galactic bar. In addition to coordinating material flow, the galactic bar is a luminous region, easily recognizable when observing the Milky Way with modern telescopes. With millions of concentrated stars, the bar's light illuminates the area near the galactic core, creating a spectacular scene. These stars, diverse in size and age, offer valuable insights into different stages of the galaxy's evolution. The strong light from the galactic bar also aids scientists in identifying other features of the galaxy, from the distribution of matter to the orbital motions of stars. These observations have increasingly refined astronomical models of the galaxy's formation and evolution. A vital structure for stability and evolution. The galactic bar is not just a structural feature of the Milky Way, but a critical factor in determining the galaxy's stability and evolution. Its role in coordinating material flow, interacting with spiral arms, and radiating brilliant light from millions of stars has made the bar both a motor and a highlight of the entire galactic system. The existence of the galactic bar underscores the unity within a seemingly chaotic system like the Milky Way. It has contributed to shaping the galaxy's beauty, vitality, and stability over billions of years, making it one of the most magnificent astronomical structures humanity has ever discovered. The Milky Way is not merely a static collection of stars, but a dynamic cosmic factory where new stars are continuously born. So, which regions in this galaxy are shaping the future of stars, and how does cosmic dust, a seemingly insignificant material, play a crucial role? Star-forming regions, also known as stellar nurseries, are vibrant and energetic areas in space where new stars are formed from massive clouds of gas and dust. These regions are not only the cradle of young stars, but also a treasure trove for scientists seeking to decode how our galaxy has evolved over billions of years. In these star-forming regions, interstellar gas clouds, primarily composed of hydrogen, begin to collapse under the influence of gravity. As the density increases, the gas cores grow progressively denser, creating high pressure and temperatures at their centers. When the temperature surpasses approximately 10 million degrees Celsius, nuclear fusion ignites, converting hydrogen into helium and releasing immense energy. This marks the birth of a star. These young stars are often surrounded by disks of dust and gas, which can give rise to future planets, making star-forming regions one of the most exciting places to study planet formation. One of the most notable star-forming regions in the Milky Way is the Orion Nebula, an area observable even with small telescopes. Here, radiant young stars illuminate the surrounding gas clouds, creating a stunning spectacle. Beyond the Orion Nebula, the Galactic Center is another hotspot for star formation. Temperatures here range from -223 degrees Celsius to 327 degrees Celsius, sufficient to trigger the birth of massive luminous stars. Additionally, the Galactic Center is home to peculiar phenomena like supernova explosions and a supermassive black hole, adding complexity and intrigue to the region. Star-forming regions are not static environments. They are constantly changing under the influence of various factors, particularly shock waves from nearby supernova explosions. These explosions generate immense pressure, triggering the collapse of surrounding gas clouds and promoting the formation of new stars. This phenomenon not only increases the number of stars, but also creates successive cycles of star formation, driving the continuous development of the galaxy. Viewed from Earth, star-forming regions are natural works of art, glowing with light and color when observed through telescopes. However, their value extends beyond their beauty to their potential to provide profound insights into the universe. Studying these regions helps scientists understand how heavy elements like carbon and oxygen are formed and distributed throughout the galaxy, providing the basic materials for life. They also shed light on the evolution of stars, planets, and the galaxy itself. Star-forming regions symbolize the vibrancy and energy of the universe. They are not only the birthplace of stars, but also natural laboratories where complex physical and chemical processes occur, playing an essential role in the galaxy's evolution. With advancements in observational technology, from the Hubble Space Telescope to James Webb, we are getting closer to uncovering the mysteries hidden within these regions. This not only broadens humanity's perspective on the universe, but also inspires a sense of connection between us and the stars. Nebulae and dust clouds in the universe are immense natural laboratories where complex physical and chemical processes occur, contributing to the formation and development of new stars. These regions, densely packed with gas and dust, serve as primary sources of material for the creation of star clusters and planets, while also giving the galaxy its mystical beauty. Among the most famous nebulae, the Orion Nebula and the Eagle Nebula top the list for their spectacular appearance and scientific significance. The Orion Nebula, located about 1,344 light-years from Earth, is one of the most observable star-forming regions from our planet. It is a stunning cosmic tableau, with radiant gas clouds illuminated by young stars within. This area not only produces new stars, but also serves as a laboratory to study how stars are formed and evolve. The Eagle Nebula, renowned for the Pillars of Creation image, exudes a surreal beauty. These pillars are dense gas clouds shielding young stars forming within. From a dynamic and optical perspective, this area demonstrates how synchronized processes contribute to the recycling of material and the sustenance of the cosmic life cycle. Cosmic dust clouds are an indispensable part of star formation. Tiny dust particles, merely a few microns in size, play a critical role in providing material and shielding young stars from intense radiation in their surroundings. These particles often contain complex compounds like silicates and carbon, creating a unique chemical environment for young stars to develop safely. Furthermore, cosmic dust acts as a reservoir for heavy elements such as iron and nickel, which are produced in supernova explosions. Nebulae are not just nurseries for new stars, but also repositories, preserving remnants of supernova explosions. When a massive star reaches the end of its life, it often explodes, releasing heavy elements like carbon, oxygen, and iron into space. These elements are then recycled within nebulae, contributing to the formation of the next generation of stars. This process sustains a cosmic life cycle in which no material is ever lost, but is continually reused. Nebulae and dust clouds in the universe are masterpieces of nature, not only offering breathtaking views through telescopes, but also holding profound scientific importance. They are vital areas for maintaining the vibrancy of the galaxy and providing invaluable clues about the origins and evolution of the universe. With future advancements in observation techniques, such as those from the Hubble and James Webb Space Telescopes, we will uncover even more wonders about these unique laboratories in the Milky Way. Cosmic dust, though small and often overlooked, plays a crucial role in sustaining and developing the Milky Way. These tiny particles are not just minute bits of material scattered throughout the universe, but are essential components in creating and maintaining fascinating astronomical phenomena. One remarkable characteristic of cosmic dust is its ability to absorb light from nearby stars and re-emit it at longer wavelengths, often in the infrared spectrum. This process not only alters how light travels through regions of the Milky Way, but also enables astronomers to observe areas where visible light cannot penetrate, such as star-forming regions or dense dust clouds. Infrared data gathered from cosmic dust have opened new observational windows, allowing us to better understand the physical and chemical processes occurring in the galaxy. Cosmic dust does more than absorb and re-emit light. It also plays a vital role in cooling gas clouds in star-forming regions. When dust absorbs energy from its surroundings, it emits infrared radiation, reducing the temperature of gas clouds. This cooling process is essential for the gas to compress more easily under the influence of gravity, thereby kickstarting the star formation process. Without cosmic dust, star-forming regions might not become cool enough to initiate this cycle, making star formation more challenging. Beyond its physical roles, cosmic dust serves as a natural chemical laboratory, facilitating reactions that create complex molecules. On the surfaces of dust particles, atoms of hydrogen, carbon, and oxygen can combine to form molecules like water, methane, and other organic compounds. These molecules are not only precursors to life, but also evidence of the galaxy's chemical richness. Complex organic molecules can be transported across different regions of the galaxy, supplying materials for newly forming star systems and planets, thereby contributing to the chemical evolution of the universe. Although it constitutes only a small fraction of the Milky Way's mass, cosmic dust acts as a bridge between generations of stars in the galaxy. When a massive star reaches the end of its life and explodes as a supernova, it releases heavy elements like carbon, oxygen, and iron into space. These elements subsequently accumulate in dust and gas clouds, forming the raw materials for the next generation of stars. This cycle not only sustains the vibrancy of the galaxy, but also enriches the chemical diversity of the universe. Cosmic dust is not just a significant factor in astronomical phenomena, but also a key to understanding the history and structure of the galaxy. Research on cosmic dust, using space telescopes like Hubble and James Webb, has provided deep insights into how stars, planets, and even life might form and develop. Understanding the role of cosmic dust helps answer fundamental questions about the origin of the universe, while opening up opportunities to explore unsolved mysteries. Cosmic dust, though small and often underestimated, is indispensable in the galaxy's operations. From absorbing and re-emitting light, cooling gas clouds, and creating complex molecules to linking generations of stars. Cosmic dust is an essential part of the universe's evolutionary cycle. With advancements in observational technology, we can look forward to uncovering even more wonders about these small but mighty particles in the future. Hidden within the vast darkness of the Milky Way is an invisible yet powerful entity: dark matter. It emits no light, no radiation, and cannot be seen with the naked eye, yet it accounts for the majority of the galaxy's mass. What makes dark matter the key to unlocking the greatest mysteries of the universe? Dark matter, one of the most enigmatic and elusive components of the universe, plays a pivotal role in the structure and operation of galaxies, particularly our Milky Way. Although it cannot be observed directly, dark matter completes the picture of the universe by influencing everything from the orbits of stars and planetary movements to the distribution of interstellar gas. According to modern studies, dark matter constitutes up to 90% of the Milky Way's mass, meaning most of the galaxy's weight resides in an invisible state. Unable to be detected through light or electromagnetic radiation, its presence is inferred through its gravitational effects. For instance, the rotational speeds of stars at the galaxy's edge far exceed predictions based on the visible mass alone, indicating the influence of a hidden force: dark matter. The nature of dark matter remains one of the greatest mysteries in modern physics. Many scientists theorize that it consists of fundamental particles such as WIMPs, weakly interacting massive particles, or axions, which interact very weakly with ordinary matter. This makes studying and modeling dark matter particularly challenging. No existing device can directly detect or observe dark matter. Instead, experiments rely on indirect evidence of its effects on visible objects. The dominant presence of dark matter sheds light on many crucial aspects of the universe's development and structure. For example, cosmological simulations have shown that dark matter acts as a gravitational framework, enabling galaxies to form and evolve since the early universe. Without dark matter, stars and planets might not have coalesced into the large-scale structures we see today. Dark matter not only shapes the structure of galaxies, but also plays a critical role in the universe's future. Research into dark matter provides essential clues to answer major questions like: will the universe expand forever or collapse back into a single point? Dark matter, with its immense gravitational pull, could slow the expansion of the universe or even reverse it in the distant future. Moreover, dark matter emphasizes that what humans can observe with the naked eye is just a small fraction of reality. Like the tip of an iceberg, what we see accounts for only about 10% of the Milky Way's actual mass. These discoveries not only lay the foundation for a deeper understanding of the universe, but also encourage humanity to push the boundaries of knowledge, uncovering wonders hidden in the darkness. Dark matter is indispensable for maintaining the structure and stability of the Milky Way. Without this mysterious substance, our galaxy would not retain its distinctive shape and balance. Over billions of years, dark matter has become the backbone of the Milky Way, ensuring that stars, planets, and clouds of gas and dust work together in harmonious order. One of the most prominent roles of dark matter is to protect stars at the edges of the galaxy from instability due to centrifugal forces. Stars far from the galactic center often move at high speeds, generating centrifugal forces much greater than the gravitational pull of the galaxy's visible mass. This should theoretically cause these stars to fly away, but thanks to the enormous mass and strong gravitational force of dark matter, the stars remain in stable orbits. This explains why the rotational speeds of stars at the galaxy's edges remain nearly constant, contrary to predictions based solely on visible matter. In addition to stabilizing peripheral stars, dark matter also shapes and envelops the galaxy by creating a structure called the dark halo. Unlike visible objects concentrated in the galactic disk, dark matter is distributed in a vast halo surrounding the Milky Way, extending up to 2 million light-years. This halo far exceeds the boundaries of the galactic disk and acts as an invisible shield, connecting different parts of the galaxy. The dark halo allows the Milky Way to maintain its characteristic shape despite external cosmic forces. Dark matter's influence extends beyond the Milky Way, interacting with neighboring galaxies. Smaller satellite galaxies, such as the Large and Small Magellanic Clouds, are strongly affected by the Milky Way's dark matter gravitational pull. These interactions alter the orbits of satellite galaxies and create elongated streams of material connecting them to the Milky Way. Over time, these streams contribute to the galaxy's mass and help reshape its structure. The importance of dark matter surpasses what we can directly observe. With its powerful yet invisible gravitational force, dark matter serves as the skeleton that maintains the balance of the entire galaxy. It ensures that stars and planets do not spiral into chaos, while gas clouds and other structures remain in a stable equilibrium. Furthermore, dark matter has been critical in forming and developing galaxies since the early universe. Cosmological simulations show that dark matter acts as the glue that binds galaxies together, shaping them into the forms we observe today. The mysterious presence of dark matter reminds us that most of the universe lies beyond our direct observation. What we see is just the surface, while the true governing force is hidden in the darkness. With its roles in protection, connection, and balance, dark matter occupies a central position in determining the destiny of the galaxy and the universe itself. The study of dark matter is not just an exploration of the Milky Way's structure and function, but also an effort to expand our understanding of the universe's most fundamental laws. Dark matter, with its invisible nature yet profound impact, challenges human imagination and technology to illuminate the mysteries enveloping space. One of the most important methods of studying dark matter is observing the orbits of stars. Astronomers have observed that, at the Milky Way's edges, the rotational speed of stars remains constant instead of decreasing as expected, based on the gravitational pull of ordinary matter alone. This phenomenon can only be explained if a massive amount of invisible matter, dark matter, is providing the additional gravitational force needed to keep the stars in orbit. This is direct evidence of dark matter's indispensable role in maintaining galactic structure. Additionally, the mass distribution within the galaxy provides valuable insights into dark matter. By measuring the movements of stars and interstellar gas, scientists have discovered that dark matter is not concentrated at a specific point, but is distributed throughout the Milky Way. Models suggest that dark matter density is highest near the galactic center and decreases outward, forming a massive spherical structure surrounding the galactic disk. This structure, known as the dark halo, extends far beyond the stars and planets and acts as a protective layer that stabilizes the entire galaxy. Beyond space observations, scientists also conduct direct experiments on Earth to detect traces of dark matter. Advanced instruments like Lux Zeppelin and Xenunt are housed in deep underground laboratories to minimize interference from cosmic radiation and other noise. These devices are designed to detect the extremely rare interactions between dark matter and ordinary matter. Although no definitive results have been achieved so far, these experiments are narrowing the search and providing valuable information about the properties of dark matter. Efforts to study dark matter go beyond understanding the Milky Way. They also open doors to unraveling larger cosmic mysteries. Dark matter is thought to play a crucial role in the formation and evolution of galaxies, and in governing the expansion of the universe. Understanding how dark matter interacts with ordinary matter could help answer core questions. How did the universe begin? How are galaxies formed and organized? And ultimately, what is the fate of the universe? Moreover, research into dark matter inspires bold ideas about new physical phenomena and even forms of matter that have never been discovered. The enigmatic nature of dark matter has driven global collaboration among physicists, astronomers, and engineers, from space observation projects like the James Webb Telescope to underground experiments. This cooperation not only accelerates research progress, but also demonstrates unity in the quest to uncover the universe's greatest secrets. In conclusion, dark matter is not only the key to understanding the Milky Way, but also a gateway to fundamental physical laws and the origins of the universe. This journey of discovery provides deeper insights into space and inspires humanity to transcend its limits, to seek knowledge within the infinite darkness of the cosmos.